Okay, so let's move. Today, we need to introduce a new quantity, inductance, right? I'm not going to lecture this in our regular lecture class, so we're going to introduce this in the recitation class. And then at the end, we will solve a few problems related to this new material. Okay, so first of all, we need to understand the role of inductance, inductors, the role of inductors in circuits, right, in our world of electromagnetism. All right, and you remember when we were introducing capacitors, right? What, a month ago, I asked the question, right? So what is the role of capacitors? And usually students, and in this semester also, usually students answer, they allow us to store charges. And that is absolutely correct, right? But I told you guys, okay, let's dive a little bit deeper and present the role of capacitors in a slightly different way, in my opinion, in a deeper way. Capacitors allowed us to store energy in the form of the electric field, right? In the form of the electric field. And now we can introduce the role of inductors in a very similar way. So now we can say inductors allows us to store energy, but now in the form of the magnetic field. So now basically the role of a capacitor and the role of an inductor are similar, but capacitors play this role in the world of electricity. They allow us to store energy in the form of the electric field. Inductors play this role in the world of magnetism. They allow us to store energy in the form of the magnetic field, right? But otherwise, the roles are similar. They allow us to store energy, and then later we can use that energy, right? Okay, so that's the role, and that's what I wrote here. Inductors store energy in the form of a magnetic field. Okay, now after this, we can actually introduce a definition of inductance. All right, and I'm going to introduce inductance in a very similar way, like we introduced capacitance and then resistance. I already mentioned several times this semester, so there are lots of similarities between capacitors, resistors, and now inductors, right? So you remember how I introduced capacitance. So we had two electrodes, right? I would dump some charge, right? Plus Q minus Q, no, 5 plus 1 coulomb minus 1 coulomb, right? Of course, it creates the potential difference, right? You increase charge, potential difference goes up. You increase charge more, potential difference between the electrodes goes up more. But if you take a ratio, charge versus the potential difference, that number is going to be exactly the same, of course, if you don't change the system, right? So that's how, and if that ratio stays the same, it's a clear indication that that quantity, that is some intrinsic property of the system, right? And then we just gave a cool name, right? Capacitance. So that's how we introduce capacitance. Then in a similar way, we introduce resistance. So if you have a piece of a resistor, right? So you apply potential difference, delta V. Of course, as a result, current starts flowing. You increase the potential difference, current goes up more. But again, if you take a ratio, potential difference versus current produced by that potential difference, that ratio is going to be exactly the same, right? And okay, so it's again a clear indication that that is some intrinsic property of that object. Okay, we gave it a cool name and we call it resistance. And now we're going to introduce in a similar way inductance, again as a ratio of something versus something. Okay, so now in order to introduce inductance, let's just take coil, for example. It's one of the typical representative of inductors. So let's take, let's say this is my some coil, right? And of course, let's assume that current flows in, current goes out, right? So we have current in. Then, of course, this current is going to create a magnetic field inside. And in your quiz number 5, you calculated the expression for the magnetic field inside of a solenoid, right? So, of course, magnetic field will be created, B. Right, so, and of course, B equals, you remember, mu naught Ni. So, B is proportional to current. Then, next step. Of course, we have loops. Basically, what is solenoid? Solenoid is just a bunch of loops positioned next to each other, right? And so, since there are many loops and there is a magnetic field, so there will be some net flux, which is of course going to be proportional to B. So flux is proportional to magnetic field. The magnetic field is proportional to I. So it means that our flux, total flux through the solenoid, through this system, is going to be proportional to the current. So now we can play the same game, right? I can increase current, flux goes up. Increase current more, flux goes up more. But again, if you look at the ratio of the flux, total flux through the system versus current, it is going to be exactly the same number over and over again. It doesn't matter how much current you drive, right? Okay, so it means that that must be some intrinsic property of the system. And now it's we just need to give it a nice or cool name, and we're going to give a name inductance, right? So that's how we're going to introduce inductance. So as a result, I can write inductance, and we're going to use letter L capital. L capital, inductance. By definition, it's a ratio of the total flux. M, magnetic stands for magnetic, right? Total flux through the system divided by the current, right? So that's what flux by definition, right? Again, capacitance, we introduced the ratio of charge versus potential difference. Resistance as the ratio of potential difference versus current. And now inductance, L capital, as the ratio of the total flux through the system divided by the current. So, okay, units. Of course, inductors are used everywhere in circuitry, right? And circuitry and electronics is everywhere. So, of course, it makes sense to introduce a special unit, right, in order to simplify a life of engineers, technicians, researchers, right, and so on. So, special unit is given, Henry, right? So, the units of inductance. The units of inductance is Henry, right? Okay, oops, right? Henry, right? And of course, what is inside of Henry? You know what? I probably should write underneath Henry, right? So what is inside? It's Weber divided by amps. Weber divided by amps. So that's what and underneath I will write Henry. Okay, so special unit. Now symbol of the inductance, right? It will be something like this, right? So that's the symbol of inductance in a circuitry. Okay, so that's my first bullet. Now second bullet. Okay, this is definition of inductance in general. You can apply this general formula to find inductance of any object, right? You can find it to find inductance over some solenoid, right? Something like this, right? Or you can apply it to find inductance over, I don't know, a piece of wire, right? Or you can apply it to find, I know, inductance of me, right? You can find inductance of any object, right? Using this definition, right? But we don't want to find inductance of any object. We just want to find inductance of a solenoid. So let's apply this formula to find the expression for the inductance of a solenoid, of a coil like this, right? When we know geometry, we know the number of loops and so on, right? So let's apply this formula to find L of a solenoid. So let's find inductance of a solenoid, right? Of a solenoid. Okay, so now I will, you know what, probably I will just recycle this picture, right? Use this picture one more time. So let's assume that what is given, the length is given, of a solenoid, right? Then we are going to assume that the cross-sectional area of the solenoid is A, right? This is A. What else? We're going to assume that number of loops in this solenoid is N capital, right? And then we'll add, if something is missing, I will add later. Right, so what do we have to find? We need to find flux, total flux through the solenoid in terms of current. We need to find flux in terms of current, and then current will be cancelled, and we will be able to find the expression for the inductance, right? So let me start with the total flux, right? F sub M, total flux. So the solenoid consists of very large number of basically coils, right? So bunch of coils positioned next to each other, of course connected, right? So if we know the flux through one coil, then in order to find the total flux, we just need to multiply it by number of loops. Flux is an additive quantity, right? So total flux equals number of loops times the flux through one loop, one, right? Phi 1 flux through one loop. Okay, then of course, what's the definition of the flux? It's a dot product of the magnetic field and the area vector. Okay, area vector, it's up to us. You remember, we can position area vector this way or that way. Okay, I will align it along the direction of the magnetic field, right? To simplify the picture. So I will take the area vector, position it this way. So this will be my area vector. Okay, as a result, B is parallel to A, so dot product is just the product of absolute values of B and A. So B, A, right? So I will close my explanation box. As a result, we're getting that the total flux equals to NBA, right? National Basketball Association, right? So now you know that NBA is just a flux, right? Okay. But it's not the final point, because you remember we want to write this flux in terms of the current. Okay, so that can be easily done, because you remember in your quiz, in the last quiz, magnetic field inside of the solenoid, B equals to mu naught times N times I, where N, I hope you remember, it's a number of loops per unit length, right? Okay, so now I can introduce it here. So it will be equal to N, then instead of B, mu naught N I times cross-sectional area. And again, N, it's a number of loops and per unit length. So in order to find N small, we just need to take N capital and divide it by the length of the loop, right? So let me insert it. So N equals to number of loops divided by the length, right? So as a result, we will have N squared mu naught. Okay, let me start writing immediately in a nice form. Mu naught N squared, then area A, then divided by this L, N times current, right? So that's what our that's the expression for the total flux through this solenoid. And again, so what's the inductance by definition? It's a ratio of the total flux divided by the current. So let's just take this current to this side, and we will get the expression for the inductance of a solenoid. Right? So now, as a result, inductance, it's a total flux phi m divided by I. It will be equal to mu naught N squared times A divided by the length of the solenoid. So that's the inductance. Okay, let me write L here on this side and frame it. So that's the formula for the inductance of a solenoid. Okay, so, and now let's analyze it quickly. Does it depend on the magnetic field? Nothing, no. Electric field? No. Current? No. Not a single electromagnetic quantity. It depends on what? Mu naught. Basically, it describes, it's a universal constant which describes magnetic properties of a vacuum. So it basically tells us that inside of our solenoid, there is a vacuum. right? If you fill that space with some material, this constant will be changed to some mu, right? Which you can get from the books. Then n, number of loops, basically geometry. Then a, cross-sectional area of the loop, again geometry. L, geometry. So you see, again, it all depends on the geometry. So if you build your solenoid, you can measure all these quantities and you can label it immediately. So you see, again, it's very similar to the properties. Okay, when it's very similar to the when we introduce a formula for the capacitance of a parallel plate capacitor. We had also that capacitance depends only on geometry. Then we also introduced the expression for the formula for the resistance of a resistor, right? Again, it depends only on geometry and the material which is made of, right? So lots of similarities between these three elements: capacitors, resistors, and now inductors. Lots of similarities. Okay, so now, okay, let me write. So it depends on geometry. It depends on geometry of the system. Again, if you build it in your garage, you can label. Okay, so now next, very important things. Okay, so it was the first bullet, second bullet, and now probably the last bullet in this in this introduction of a new material. Now let's find the potential difference across a solenoid, right? Potential difference across a solenoid, and of course it can be surprising. Which potential difference are we talking about? Solenoid, it's basically a piece of wire. And in this case, we assume it's a piece of an ideal wire. So basically, it means that it doesn't have resistance. So far, all the time, potential difference was created by what? A battery, for example, right? Battery creates the potential difference. So this is just a piece of wire. There's no battery, right? Then, of course, the potential difference can be created if, for example, your piece of wire has some resistance. And of course, it will work as a resistor, and we can calculate the potential difference as IR. But in this case, we assume it's an ideal piece of wire. Where is the potential difference? And that can be mind-blowing, right? And so the only candidate which can be, the only formula or the phenomena which can be used now to explain any possibility of having the potential difference in this system, it's a Faraday's law, right? It's a Faraday's law. Let's apply Faraday's law to find the potential difference across a solenoid. Okay, so let me write. So potential difference, which we wrote across an inductor. Let's find potential difference across. Okay, I will just write L, inductors, across an inductor. And so yeah, Faraday's law. EMF equals to negative rate of change of the magnetic flux. You remember, for the last 3 classes, we've been using this Faraday's law many times. Okay, so what? Now we can write total flux in terms of the inductance, right? So, of course, let me open explanation box. Phi m equals to L times I. So let's plug it. L is the constant, right? We assume that you pick a certain inductor, right? Inductance, right? Okay, so since L is constant, of course, we can take outside of the sign of differentiation, right? As a result, you will end up with minus L and derivative of the current with respect to time, rate of change of the current. Okay, so now it's not 0, right? So now we're getting some, under certain conditions, we can get the we can get the potential difference. Again, it's a mind-blowing, right? Okay, I understand the physics, right? But it's still so interesting, right? So if you have, again, if you take a piece of wire, ideal piece of wire, assume that there is no resistance. If you position it like this, then you are not going to have any potential difference across this piece of wire. But if I reshape it, if I just create a solenoid, if I just wrap it around some cylindrical surface, for example, this marker, right? If I create a structure like this, okay, let me push them, right? If I create the structure like this, basically solenoid, okay, and now if I start driving current through this structure, now there will be potential difference, okay, under certain conditions. Which conditions now we're going to discuss, right? So I just changed the shape. Before I had this just a straight piece of wire, and in that case we're not going to get potential difference. But once I wrap it in this form, in this shape, as a solenoid, as a solenoid, right, as a coil, okay, now we're going to get some potential difference. So let's see under which conditions we can get the potential difference. Right, so probably I'll move to this side, right, because now I will need some space. And first, I will put small bullet, and I will start with the easiest case. What if current is constant, right? So what if, all right, I will write if I is constant. What if current flowing through your coil, through your solenoid, doesn't change in time? Okay, then di over dt are obviously 0, and EMF or potential difference created, you know what, probably I will just, let me just write delta V, all right? Let me write it. Okay, delta, but EMF, it's a potential difference, right? So let me write delta V equals to minus L di over dt, right? And now let me frame it, because that's the formula for the potential difference across a solenoid, Okay, so now if current is constant, what will be the potential difference? Potential difference is going to be 0, right? So in this case, delta V is 0. Okay, delta V, delta means the value of, in this case, the value of the electric potential at the final point minus the value of the electric potential at the initial point. Which point is final, which point is initial? Okay, here current enters, right? So that will be our initial point. So that will be our initial point. At this point, current leaves the solenoid. That will be our final point. So delta V in this case, V final minus V initial. In this case, if the current doesn't change in time, potential over here and potential over there is exactly the same. Basically, in this case, solenoid doesn't do anything, right? It's just a piece of wire. Okay, so delta V equals 0. Now, the next case, what if current increases, I think, yeah. Let's assume the second case. What if current increases? So basically in this case, di over dt increases, right? Positive. Di over dt positive, right? And as a result, di over dt positive, L is positive all the time, right? Inductance cannot be negative, right? And minus in front. So this is positive and minus in front. As a result, potential difference is negative. As a result, delta V is negative. Again, what does it mean, delta V? It means that V final minus V initial is negative, and it means that the electric potential at the final point is going to be smaller than the electric potential at the initial point. So I can write something like this. So V final is smaller than V initial. Okay, now I want to draw the picture in order to see what actually happens. What happens in the circuit. Okay, I will assume the simplest possible circuit, just a solenoid and the battery. Okay, so let me draw something like this. So let's assume that this is my solenoid, right? Yeah, solenoid, and then there is a battery. So it is connected to a battery. Let's say positive electrode, negative electrode, right? So that's plus minus, right? Okay, that is the solenoid, and this current, which increases, right, is produced by these batteries. So there is a original current flows this way. So that's our current which increases. Right. So now this current increases. As a result, what happens inside of the solenoid? So solenoid responds somehow to this change in the current by producing this potential difference, right? So again, V final is smaller than V initial. Again, you remember which point is final? The place where the current exits, right? So that is our final point, right? And that is our initial point. And the electric potential at this point is smaller than the electric potential at this point, right? So I can draw something like this. Over here we're going to have plus, smaller, there should be minus. Right, so I can draw it here minus and here plus. And you need to understand, it's a this potential, it's a response of the solenoid. Solenoid produces its own potential difference. Okay, so this battery produces its own distribution of the potential, right? Somewhere here potential higher, then it's going down. No, this is production of a solenoid, right? So this original current increases. As a result, the solenoid responds with this additional potential difference, right? So this potential difference is made in the solenoid, or is made by the solenoid, right? So at this point, electric potential is smaller. Here, the electric potential is higher. Okay, and now in order to basically, I can say that this solenoid works as the, basically we can think of it as some small battery, right? So with this polarity, right, plus and minus. And as a result, so since this solenoid starts working basically like a battery producing this potential difference, of course there is no battery right inside of the solenoid, but it works. Since it produces potential difference, we can say, okay, it works as a battery, right? And of course, battery with this polarity. So as a result, since it produces additional potential difference, there will be current, additional secondary current, which we called, of course, induced current. And what's the direction of that induced current? From this plus to that minus. So in this circuit, it is going to draw this current. So I induced. All right. So the solenoid will drive its own additional current in the opposite direction to the original current, right? So again, you over here with this battery, you increase the current, this original current. Solenoid sees that, it doesn't like that the current increases, and as a result, it produces potential difference. Here, potential is lower than here, and as a result, basically, again, as I said, it starts working as a small battery, and as a result, it starts driving secondary induced current in the opposite direction to the direction of the original current. Again, because basically, what is behind that? It's a Faraday's law. That Lenz's rule, you remember our philosophical description of the Lenz's rule, that the system doesn't like changes. And that's what happens. In this case, solenoid doesn't like changes in the original current. Original current increases. The solenoid, I don't like it. I will try to rebel. I'm going to resist that. It starts driving induced current in the opposite direction, so that this growth of the original current will be somewhat suppressed. Right, somewhat suppressed. Of course, it wouldn't be able to suppress it completely, no way. But it will reduce the growth, right? Of course, you can say, okay, at the expense of what? The solenoid is going to drive this induced current. You remember? Inductors allows us to store energy. that energy, that small amount of energy which is stored inside of the inductors, will be used to drive this induced current in the opposite direction in order to reduce the growth of the original current. Right? Again, it's just basically Faraday's law behind that. Right? And we just apply it for circuitry. Okay, so let me probably write something. I will write this conclusion. So I induced try to suppress I original. So let me write underneath. So I induced tries to suppress the original current. Okay, the growth of the original current. Okay, it's clear. Suppress the growth of the original current. Current. Right. Again, the system doesn't like changes. Right. Again, the same philosophical idea that the system doesn't like changes. Okay, and obvious sort of application of this. Right. Imagine some arbitrary circuit. It doesn't matter which circuit, right? Let's say first the switch is open in the circuit. Of course, there is no current in the circuit, and then at a certain moment of time, let's say you close the switch. Of course, current starts flowing in the circuit, and of course, if you don't know physics deep enough, you might expect that current in the circuit just jumps from 0 value to some finite value. Let's say from 0 to 1 amp, for example, right? So if you don't know physics enough, right? Let me write first example, right? Which way I wrote, probably I will just write turning on the current, right? Turning I on, right? Turning on the current. So again, as I said, if you don't know physics deep enough, you might expect that current will just jump from 0 value to some finite value. You might expect a step function like this, right? But of course, in real life, it doesn't happen. You will never see a step function like this in the real circuit, right? What happens? Because any circuit, even any piece of wire, right? It has a certain amount of inductance. And of course, any element in the circuitry has a certain amount of inductance. So as a result, when you try to increase current in your circuit, right? All that inductance in the circuit is not going to like that. It's this case. Current suddenly tries to increase, right? The inductance inside of the solenoid is not going to like it. As a result, it will produce this potential difference, right? And it will start driving induced current in the opposite direction to the original current, which you try to drive in the circuit. As a result, right, so this induced current in the opposite direction is going to reduce the growth of this current. As a result, you're going to see something like this in real life, right? Right. You're not going to see step function every time. There will be like a smooth transition of the current from 0 value to the finite value because of the inductance in the circuit, right? Okay, so that's the first case when current increases, original current increases. And now let's look at the case when current decreases, right? So let's explore all possibilities. Now we will put a new bullet. So what if current, again, this original current, which is created by the original battery, right? If current decreases, of course, di over dt is negative now, right? Di over dt negative. So, okay, this di over dt is negative, minus in front. As a result, delta V is positive. So, as a result, I can write that delta V is positive now. And so now again, that is our final point, that is our initial point. So I can say now that, okay, you know what, I can move closer to this edge. So now I can write that V final minus V initial, it's positive, again, because delta, it's a V final minus V initial. And as a result, the electric potential at the final point is larger than the value of the electric potential at the initial point. So I can write V final is larger than V initial, right? Okay, now let me draw a similar picture now for this situation, and again I will draw a similar situation. So again, let's say this is my solenoid. This is the original battery which drives the original current, right? Again, that is plus minus. So again, that is our final point, that is initial point, right? Again, original current from plus to minus, right? So that is the current which decreases, right? And so now the solenoid, which is exposed to this change in the current, solenoid doesn't like. Let me first show the potential, all these potentials, and then I will continue talking about liking or not liking. All right, so V final is larger than V initial. So now I can draw here plus and here minus, right? So the electric potential at the end of the solenoid is going to be larger than the electric potential at the beginning of the solenoid. Again, that's the response of the solenoid. That's what solenoid produces. This battery tries to produce something its own, right? That is made by the solenoid, right? Or made in the solenoid, right? All right, so basically now I can say, again, in order to simplify explanations, I can say, okay, now the solenoid works as a small battery, but polarity now is different to what we had over here. So now I can draw something like this. So now it works as the additional small battery. Okay, maybe I can reduce this size, right? With plus here and minus there, right? So this additional battery, of course, will drive its own secondary current, induced current, but now direction of this induced current is going to be opposite to what we had over there, right? Again, so from plus to minus. So now induced current is going to flow this way, right? So that will be I induced. Okay, why I started using this idea of the small battery, additional small battery? Because quite often students get confused. At the very beginning, when I started teaching, I used to draw only plus and minus. And then as a result, many students will start driving this induced current this way, from this plus to that minus. But no, it's wrong. These pluses and minuses are produced by this solenoid, and then induced current flows through the rest of the circuit. After seeing this mistake many times, right, I decided, okay, let me add this idea of a small battery. So now the solenoid works as a small battery with this polarity and drives current, right? So now induced current is in the same direction as the original current. So again, in order to simplify the process of remembering or explanations of what happens, we can think this way. System, okay, this system, the solenoid in this case, again, doesn't like changes in current, original current. You see, current is dying, is going down. The solenoid looks at that, okay, no, I don't like it. Current is dying, I don't like those changes, I want to keep it as steady as possible. So as a result, inductor produces this potential difference and it starts driving induced current in the same direction as the original current. Now it supports. It shouldn't be a surprise for us because again, it's just Faraday's law behind this analysis, right? The same Lenz's rule, you remember the same philosophical idea, system doesn't like changes. Well, now we just apply it for a circuit, for this simple circuit. In this case, so if current is dying, right, so now the solenoid starts being supportive, starts behaving like Florence Nightingale. Okay, now I will help you. I will drive the current in the same direction so that this current will die slower. Right. In the first case, current was increasing, right? And again, the solenoid didn't like that. Now, at that case, it behaved like a rebel, right? It tried to suppress that growth, to keep the original current as steady as possible, as constant as possible. And as a result, the solenoid started driving induced current in the opposite direction to the original current to suppress that growth. Now, current is dying, system changes its attitude, and now it's being supportive. It drives the induced current in the same direction as the original current. All right? Okay, we're going to use this reasoning quite often to explain behavior of the inductor, of the solenoid. So let me check if I write. Yeah, I wanted to write this. I induce now tries to support original current. So let me write this. So now I induced tries to support original current, which is produced by the battery. Here, it drives the current in the opposite direction. Here, in the same direction. Okay. And example similar to this, right? So here we discussed what if you close the switch and current jumps from 0 to some finite value. Now let's assume what if we have a circuit, all right, with established current, and then you have a switch, and let's say you open the switch. And of course, if you don't know physics deep enough, so you might think that current will just drop dead, right? So again, it will be a step function. So first, let's say we had 1 amp, and then it drops to 0, right? If you don't know physics deep enough, you might think this way. All right. So, but if we apply this analysis, the situation will be slightly different. Again, example. Turning current off, right? Again, I will draw a similar picture. So if you have I versus time, right? So first, let's assume current was running in this circuit, right? And then at a certain moment of time, let's say you open the switch and current, again, if you don't know physics deep enough, right, you might expect this step function. But of course, in real life, it doesn't happen because this doesn't happen because any circuit has a certain amount of inductance, right? Certain amount of inductance. As a result, that inductance, when you try to, when you open the switch, current starts going down significantly, right? Current is going down. As a result, that inductance is not going to like that. It will start driving induced current in the same direction as the direction of the dying current. As a result, you're not going to get a step function. You're going to have a smooth transition, reasonably smooth transition. So you're going to end up with something like this, right? That's what you're going to see approximately in real life. No step functions. Nature doesn't like step functions, right? Okay, so that's the review of a new material, right? And now let's look at several examples. Okay, so now let's look at first example, problem 25. And again, it's from the chapter 30. I will probably erase this introduction, this part of the introduction up to this point because we will need this potential difference. Let me erase this. Right, okay, so as I said, problem 25. So what do we have in this problem? We have some inductor, solenoid. Again, most of the time we're going to use a solenoid as an inductor, right? So inductance is given. All right, inductance is given, and that is 10 milli, and units you remember of inductance, Henry, millihenry. So we have a solenoid inductor. we have an inductor with inductance. Okay, let me put it in a bracket. L equals 10 milli H, Henry. Right. Then, what else we know? We know that through that solenoid, current is flowing. And we know what happens with that current. That current is going down. Original current is 150 milliamps, and the final is 50 milliamps. So, current, which way I wrote. Okay, so let me write it this way. So, I final equals 150 milliamps, and current initial equals to 50 milliamps. Okay, so what do we have to find? We need to find the response of the solenoid. You see, we have an inductor. Current changes through the solenoid. It means that, of course, the inductor, the solenoid, will respond with a certain potential difference across itself. Again, you need to remember that this potential difference potential difference is made in the solenoid, right? Okay, like now everything is made in China. Now we can say this is made in solenoid. Made in the solenoid. So that's the response of the solenoid. So what we need to find? We need to find delta V across the solenoid. Okay, let me remind you, across the inductor. Across the inductor. Okay, this is the inductor. Okay, before we start crunching numbers, let's conceptually discuss. Are we going to, first of all, are we going to get positive or negative potential difference, right? Okay, so which case do we have? This, or that? Current changes. Definitely not the first case. If current is constant, then that solenoid doesn't do anything. It will be just useless, a long piece of wire in your circuit, right? Our current is going down. Oh, no. Initial 150. Yeah. Okay, sorry. Initial current is 150. Final is 50. Right, so this is initial current and that is final. Okay, so current is going down. So it's not this case, it's this situation. If current is going down, then what? Philosophical idea. Solenoid doesn't like when current flowing through the solenoid changes. If current is going down, then the solenoid starts behaving like a Florence Nightingale. It starts being supportive. So it will produce the potential difference so that the induced current is going to flow in the same direction as the original current, supporting the dying original current. And of course, in order to drive induced current in the same direction as the original, of course, at the end of the solenoid, at the final point of the solenoid, you should have higher potential than at the original point, so that you will have a polarity, this polarity across this imaginary small battery, right? So only in that case, induced current is going to be in the same direction as the original current. So as a result, V final is larger than V initial, so delta V is positive. So now we're just going to apply this formula, and of course we know that at the end we're supposed to get positive delta V. Again, that is delta V across the solenoid. That's delta V produced by the solenoid in the solenoid. All right. Okay. So now let's start crunching numbers. So let me separate this, and I will just rewrite this formula, and that's why I left this part, because we needed this. So delta V equals to minus L di over dt. Okay, so now I need to say, criticize to some extent this problem. This problem is not stated, let's say, not stated absolutely properly. All right. Why? They told us that current is going down from this value to that value, but they didn't tell us, the author didn't tell us, or doesn't tell us how that current changes, right? It can be linear, it can be some complicated dependence, right? So, but of course, in order to simplify the problem, we're going to assume that this current is going down linearly, right? So we're going to make that assumption. Of course, this problem doesn't tell us that, but we're going to assume, right? So I will open my explanation box and I will write that. Assume current, which we wrote I, changes linearly. I changes linearly, right? So it is going down along a straight line. If you plot current versus time. Okay, so if current changes linearly, so what can we do with this rate of change of current, derivative di over dt? We can replace it with delta I over delta t. We've done it many times in this semester and in the previous semester, right? So we can replace, basically that is the slope of curve I versus t. But of course you can, instead of using infinitesimally small delta t, dt, you can use a finite value of delta t to find the slope, and the slope will be exactly the same, right? So we can replace in this case this formula with minus L delta I over delta t. Of course this transition is only correct when current, in this case current, function changes linearly, right? Okay, so that's my small criticism of this problem. All right, and now what? We know pretty much everything, so we just need to plug and okay, now I realized what is missing, the time. The current changes in this period of time. Delta t is 10 microseconds. 10 microseconds. Okay, now we have all the information, right? So now it will be equal minus L is 10 times 10 to the power of minus 3 Henry inductance. Then, of course, this is I final minus I initial, right? So that will be final is 50 milliamp minus, right? Again, it's a I final minus I initial, right? So this is I final minus I initial, right? Minus 150 milliamps and divided by the time elapsed, 10 microseconds. So 10 times 10 to the power of minus 6 seconds, right? Minus from here, minus from there. As a result, delta V will be positive, as we discussed conceptually, right? So delta V is going to be positive. Okay, so now you can calculate it through, and you're going to end up with, I will emphasize on positive sign, so plus 100 volts. So that's the response of the solenoid again, right? So what we have some battery, right, which drives this current. So original current is 150, final is 50 milliamps. So the current, original current through the solenoid is going down. The solenoid doesn't like it, right, according to the Faraday's law and Lenz's rule, right? And it will start supporting it. Start supporting by creating this potential difference, 100 volt across the solenoid. So here we have, okay, the potential difference, this minus this, will be 100 volts. And as a result, this induced current will support dying original current, right? Okay, so that's a very simple problem, just application of the formula which give us a potential difference across the solenoid, again, created by the solenoid, right? It's a response to the changes in the original current. Okay, so now let's look at the second problem. So now the next problem. The next one is 66. Again, I will just erase this because I still need this and I need those diagrams, right? So now 66, and in this problem we're going to have a similar inductor, okay, an inductor with the same inductance. So I will just recycle this part. All right, so now it's a problem 66. So we have an inductor with this inductance, again 10 millihenry, right? Then we have some information about current is given, and that information is given in the form of the plot. current versus time. So let me plot it. All right, and then we'll discuss what needs to be found, and conceptually, and then of course numerically. So we will do all that. So current is given. Right. So that is I, of course, units of amp. Then time. So this is t, right, in millisecond. And probably first I will plot the graph, and then I will put the numbers. All right, so first it is growing, right? Then it stays constant. Then it goes down. Then it stays constant. And then, and that's it. All right. Okay, and so now the values of current here. This is 2 amp. This is minus 2 amps. Then time, let's say this is 2 units millisecond, I think, right? Yeah, milliseconds. 2 milliseconds. This is 3 milliseconds. Then this is 4. This will be 5. And this point is 6 milliseconds. Right. So that's the plot. So that's how current through the inductor. Right, so we have some inductor, right? So maybe a circuit can be more complicated, right? So there's some battery, right, which drives the this current, and that's how this current through the solenoid changes, right? So first it is growing, then stays constant, then it goes down, and then again it stays constant. Let me overlap with this 0.6. Right. Okay, so before, what needs to be found? We need to find the potential difference across the solenoid for each period of time. So what needs to be found? Let me write. So we need to find delta V, right? And of course, we're going to have different delta V's for different periods of time. Okay, before I start calculating those delta V's, right, using that formula, let's first discuss conceptually. When are we going to get delta V positive, when negative, or 0, right? So first stretch of time. You know what? Let me first label these periods of time. So this will be period 1, right, from 0 to 2. Then this period 2. This will be, okay, this whole from 3 to 5. This will be our third region, and this will be the fourth region, right? So let's look first at the first period of time from 0 to 2 milliseconds, right? So what happens with the current? Current, again, original current produced by the battery, right? By this battery, this original current is growing, right? So, okay, current is growing, it means that this case, right? If current is growing, right, so then what's the response of the solenoid? If the original current through the solenoid is growing, solenoid doesn't like it. So, and of course, as a result, it starts behaving like a rebel, right? It starts producing the potential difference in such a way so that the induced current will flow in the opposite direction to the original current, which is growing, because it tries to suppress it. All right, so it means that in order to drive the induced current in the opposite direction, so at the beginning of the solenoid must have higher potential than at the end. So delta V must be negative. So for this stretch of time, delta V will be negative. Then for this, current is constant. It's in this case, if current is constant, the solenoid is not going to produce any potential difference across itself, right? Again, you need to remember that this delta V is a production of the solenoid. That's what solenoid produces using its own internal energy. You remember, inductor allows us to store energy in the form of the magnetic field so that inductor can use that energy later, right? Okay, so if current is constant, potential difference across the solenoid is not produced. Basically, in that case, if you have a constant current, this solenoid is just nothing but just a long piece of wire. It doesn't do anything in the circuit. It's just a useless element. So here, potential difference will be zero. Then here, current is going down. So if current is going down, it's in this case, right? Current is going down, so the solenoid doesn't like that original current is going down. So now it starts behaving like a Florence Nightingale, and it starts supporting it. It will produce the potential difference in such a way so that the induced current will flow in the same direction as the original current. And of course, in order to get this induced current at the end of the solenoid, we must have higher potential than at the beginning. So basically, again, as I said, solenoid in this case starts working as a small battery with this potential, with these electrodes, right? Positive electrode on that side and negative electrode on this side. So as a result, it starts driving current in the same direction as the original current. And of course, delta V is positive. So for this stretch of time, but delta V will be positive. And for the last one, current doesn't change, although it's not small, right? 2 amps of current, but who cares? Okay, solenoid doesn't care, right? If current is constant, and it doesn't matter, it can be huge. You can have, 100 amps of current, but if current is not changing in time, potential difference across the solenoid is not going to be produced, right? Okay, so that's conceptually, and now let's calculate those potential differences, right? And let's start with, probably first I will just rewrite this formula, right? I will rewrite this formula. So delta V equals to minus inductance and di over dt. Okay, so now of course I don't have to make an assumption, right, because I see all these how current changes with time. I can see current changes with time linearly. As a result, di over dt can be replaced with delta I over delta t, right? So I can write this as minus L delta I over delta t. Okay, basically it's minus L I final minus I initial divided by delta t. Of course, t final minus t initial. Time doesn't go back, right? So we don't have time machines. Right, so that's what we need to apply. Let me put maybe brackets over here. That's what we need to apply for each of this region, 1, 2, 3, and 4. So let's start with region number 1. Okay, I guess I can now erase this because now I rewrote this formula. All right. So region number 1, so I can write delta V with subscript 1. Right. Again, it's not current, it's just a Rome digit 1. So it will be minus. Okay, I will start plugging numbers immediately. So 10 millihenry. 10 times 10 to the power of minus 3 Henry. Then, for the region 1, final current, this, right, 2 amps. Initial current, 0. So it will be 2 amps minus 0 amp divided, what's the stretch of time? And don't forget the time is milliseconds. So it will be 2 minus 0 milliseconds. 2 minus 0. Okay, let me write explicitly times 10 to the power of minus 3 seconds. Right? So this difference is going to give us plus, minus in front, so delta V is negative, and that's what we discussed, that's what we got discussing conceptually. Okay, what will be the answer? In the region 1, delta V will be minus 10 volts. Right? If you multiply it through, you will get negative 10 volts. So that will be the potential difference again between it's this case current is growing, so the potential difference between this point and that point is negative, right? Minus 10 volts, right? So the electric potential at the beginning of the solenoid is going to be larger than the electric potential at the end of the solenoid. Again, it is this potential difference again is produced by the solenoid. So now next one, the second region. You know what? I also had to plot it. Let me plot it here. Right. So this will be delta V versus the same time, right? And 1, 2, 3, 4, 5, 6, right? So let's say 1, 2, 3, 4, 5, 6, right? Okay, so over the first stretch of time from 0 to 2, the potential difference is negative 10. Right, so let me put here, let me estimate the space in amount of, right, so it will be negative 10, right, so from 0 to 2, right, so that's the first, right, potential difference over this stretch of time from 0 to 2 millisecond, potential difference is negative 10 volts. Now the second region, this, okay, obviously current stays constant as a result. Since I is constant, so immediately delta V over the second region is 0, right? So I will, it's from 2 to 3, okay, so dash line, and now it will be 0. The third region, right, over the third region, again I will just, okay, now it's not going to be 0, right, so I will write delta V, the third region, equals minus, I will start writing numbers immediately, right, it's obvious, again, 10 times 10 to the power of minus 3 Henry, right, minus L, and now final minus I initial. Final, this point, right, at the final moment of time, the current is minus 2 amps. So over here I will write minus 2 amps. Then minus because of the formula, because it's a delta I, final minus initial value of the current, so minus, and the initial current 2 amps. So it's minus 2 amps, and divided by the stretch of time 5 milliseconds minus 3 milliseconds. So 5 minus 3 times 10 to the power of minus 3 seconds. Right? Okay, minus from here, minus from there, plus. So the potential difference is going to be positive, as we discussed conceptually. And if you multiply it through, you will get plus 20 volts. Right. So now over this stretch of time, over this period of time, current is potential difference is positive, right? So so let's say this is 10, this is 20. 10, 20. So it's from 3 to 5. So let me draw this dash line. From 3 to 5, it will be constant. Right. And the last, okay, again, current is constant. If current constant, the solenoid doesn't do anything in the circuit. It's just a useless piece of long wire. So region number 4. Right. So again, since I is constant, so the delta V over the fourth region equals to 0. Right. So the last piece in this puzzle, it will be just 0. Right. Okay. Maybe I should also remind that this T is in milliseconds, right? I was just afraid that I'm not going to have enough space, so as a result I skipped the units. Right. Okay, let me check. Yeah, that's what I was planning to discuss. And now let's look at the last example, which will be conceptual example. Okay, and the last example, it will be a conceptual question 11, part C. Let's answer that part. I guess I can erase this, right? And yeah, I can erase everything. Again, we will just need that part. So this is conceptual question 11C. Right. So what is given? Again, we have an inductor, basically some kind of solenoid, right? Inductance is given. So let me draw it here. Right, so that's inductor. Inductance L is 2H, Henry. Inductance of 2 Henry. Then we know that the original current now we label it I1. Original current I1 flows through this inductor. Right? We don't know what happens to this current I1. We actually need to answer the question, what happens to this current in time? Is it growing? Is it dying? Or is it stays constant? Or is it constant? Right? Okay, but we also know the response of the solenoid, the response of the inductor. Right? A response in terms of the creating the potential differences and so on, right? So what is given? What is given? We know that the response of the solenoid, response of the inductor, potential difference. Potential at the end of the solenoid or at the end of the inductor is higher than the electric potential at the beginning of the inductor, right? Basically, and we also know the value of this delta V. So delta V is 2 volts, right? Okay, again, something happens to this current, original current. As a result, the solenoid, the inductor, responds with this potential difference, right? So we need to answer the question, what happens to I induced? Okay, maybe I'll write underneath. So what happens to original current, right? I1 is growing or dying or constant, right? It's a conceptual. Of course, in this case, we're not going to calculate it. Okay, so in order to answer this question, we just need to analyze the response of the solenoid. But if you know the response of the inductor, you should be able to tell what happens to the original current. But you know, before I start analyzing the response of the inductor, let me sort of complete the circuit. Of course, the circuit can be more complicated, right? So, and this is just a small part of the complicated circuit. But let me just draw a very, very simple. So let me complete it. So this original current can be produced by some initial battery, original battery, right, which drives this current I1. So here, wrong polarity. So this should be positive, this should be negative, right? So this is plus, this is minus. So this battery drives this original current, right? Then, so response of the solenoid, plus and minus. Again, I usually just use this small imaginary battery. So response of the solenoid to the changes in this current. So it responds with this additional battery, plus minus, right? So this battery, right, these polarities, of course, will drive the induced current this way, right? So it will be this way, this way. So that will be our I induced, right? With this polarity, which is given, right? Induced current will flow in this direction. Okay, so since induced current, okay, it's here also, right? I induced, right? Since induced current is in the same direction as the original current, it happens only when original current is dying. In this case, the solenoid sees that fact. Okay, original current is dying. Okay, I will support you. Right, behaves like a Florence Nightingale. In this case, it creates the proper potential difference, so that the induced current flows in the same direction as the original current. Right. So I can write, so as a result, since I induced is in the same direction, flows in the same direction, in the same direction as the original current, right? So we can conclude that by just looking at the potential difference that inductor creates, right? Plus and minus. So as a result, induced current is in the same direction as the original. Since this is true, so then we can say that I1 is going down. I1 is going down. Okay, is decreasing. Let me write, is decreasing. Is decreasing. Right. So in this case, it's this situation, right? So when current is going down, the inductor becomes supportive, right? And it drives current in the same direction as the original current. If we had an opposite situation, let's say plus here, right, minus there, okay, in that case, again, we would have positive polarity on this side, positive electrode here, negative electrode over there, and of course, as a result, induced current would flow in the opposite direction. It can be only in the case if the original current is growing, right? If original current is growing, the response of the inductor, it creates such a potential difference, so that the induced current will flow in the opposite direction to the direction of the original current. Right? Okay, so basically it's a conceptual question. Sometimes I give questions like this on the exam. So by just analyzing the response of the solenoid, you should be able to tell immediately what happens to the original current. Right? Okay, it should be enough for today, and thank you, and I'll see you next time.